Okay, let's unpack this. Have you noticed all the noise around AI lately? It's
Well,
well, one minute the headlines are screaming about thinking machines,
right.
right?
Absolutely.
And then like the next minute someone you trust is saying, "Hold on, AI can't think at all." It creates this real whiplash, this dissonance, for anyone just trying to figure out what's actually happening.
It really does.
Yeah.
Because you see these incredible demos. I mean, the fluent text, the chatbots, it seems so helpful. It feels intelligent.
Yeah, it does.
But then you hear the counter arguments, the limitations, and it leaves you wondering, okay, what's hype and what's real here?
Mm-mm.
And that tension, actually, that desire to get past the surface claims, that's kind of what motivated some researchers over at Apple recently.
And that's our source material for this depth dive today. A really, I think, genuinely fascinating study from that Apple team. Their core question wasn't simply, did the AI get the right answer? It was something much deeper.
Yeah, more probing.
Can we actually peek inside the process, the supposed thinking steps, to see how it gets there?
Right. They wanted to look beyond just the final, often quite polished output, find a way to really stress test the AI's underlying reasoning ability. And the way they did it was, well, brilliant, almost old school.
Using puzzles. Right.
Exactly. Classic, deceptively simple puzzles.
Yeah, I saw that. Things like Tower of Hanoi, checker jumping, river crossing, blocks world, stuff you might remember maybe from logic games or intro CS classes.
But the key thing here is you can tune their complexity very precisely.
Ah,
You can start super easy, trivial easy, and then just crank it up. One small step, one more disk, one more checker.
right. So they become like controlled experiments.
Precisely. The researchers use these puzzles like diagnostic tools, almost like X-rays for the AI's mind, if you will,
An X-ray, I like that.
designed specifically to expose limitations in reasoning that might stay hidden if you just ask it to, I don't know, write a poem or summarize an email. They want to see exactly where and how the AI's thinking starts to break down when you put it under real measurable pressure.
Okay, so they set up these stress tests using these large reasoning models, the kind we hear a lot about, often the ones that use chain of thought.
That's right, where the model kind of narrates its steps as it goes along, tries to show its work, essentially.
So take Tower of Hanoi, moving those disks.
Yeah, one disk. Easy. Two disks. A few moves. But, as you add more disks, the number of required moves just explodes. It grows exponentially.
And they did this with several different types of puzzles, right? Always scaling the complexity from dead simple up to incredibly hard. And they just watched how these AI models perform.
They did. And what they found was, well, really striking. Across different models from different major builders, they all showed a surprisingly similar, predictable pattern of performance as that complexity dial was turned up.
Okay, so what was that pattern?
Well, they identified these distinct complexity regimes, as they call them. At low complexity, the really easy puzzles, something surprising happened.
Oh.
Yeah, the traditional language models, the ones that just give you a direct answer without showing all the steps, they often did better.
Really?
They were faster, for one, and they used way fewer tokens. Tokens being the little pieces of language that the AI processes. They didn't get bogged down in these long, sometimes unnecessary internal monologues.
Okay, so for the simple stuff, lean and fast wins. Makes sense. What about when things get a bit trickier?
Ah, that's the medium complexity range. And this is kind of the sweet spot. This is where those chain of thought models really shine.
Right, this is probably where most of those impressive demos we see come from.
Exactly. They generate these long, detailed rationales, exploring possibilities, sometimes even seeming to catch mistakes and self-correct. It really feels like thinking is happening here.
Yeah.
And crucially, they often solve these medium difficulty puzzles correctly.
All right, so they master the medium stuff. That sounds pretty good. But then,
It feels about to come
and
over.
then
Yeah.
you push the complexity just a little bit further. You add one more disk, maybe one more constraint, and you hit the high complexity regime. And this is where it gets, well, really interesting and, frankly, a bit grim, as the paper puts it.
Graham.
How so? Performance doesn't just sort of degrade gracefully. It doesn't just get a bit worse. It collapses. It falls off a cliff. Accuracy plummets. Sometimes it even drops below what you'd get by just guessing randomly.
Whoa, just nosedive.
Precisely. A sharp, sudden drop. And here's the really counterintuitive part. At this high complexity, the models often start generating fewer tokens.
Fewer. Wait, I thought chain of thought meant more tokens, more thinking.
You'd think so, right? But it seems like their thinking process just shuts down prematurely. It gives up even when its context window, its available working memory, essentially is still wide open. It has the space, but it just stops reasoning effectively. Okay, that feels, yeah, like a huge red flag. The engine isn't just sputtering, it's stalling out completely, even when it has fuel left in the tank, so to speak.
Exactly.
So what does the study suggest is going on there? Why the collapse?
Well, the researchers point towards how these models are fundamentally trained. They're primarily trained, it seems, to produce reasoning traces, those step-by-step explanations that look plausible.
Look plausible, not necessarily be correct.
Kind of. They get rewarded during training for generating sequences of tokens that resemble human thought processes, that sound like logical steps. But the training doesn't seem to effectively penalize, or maybe penalize enough, those subtle early errors or small hallucinations that completely derail the entire logical chain later on.
Okay, so it's a bit like grading a student only on how neatly they showed their work in a math problem, not on whether the final answer was actually right. It prioritizes the appearance of reasoning over the soundness of it.
That's a great analogy. Exactly. And within these structured puzzles, this weakness shows up in a few key ways. On the easier tasks, they might find the solution path fairly quickly, but then they just keep generating extra unnecessary steps afterwards, wasting tokens, burning compute, and sometimes even introducing errors after the fact.
And on the harder tasks,
On the harder tasks, they often get stuck much earlier. They might generate repetitive loops or just nonsensical steps. They get derailed by an early mistake and just never manage to recover or find the correct path forward. The whole process just breaks down.
did the study list specific symptoms? Like, what did these failing reasoning traces actually look like?
They did. They identified several common failure modes, things like excessive redundancy, saying the same thing over and over in slightly different ways, a real inability to look more than just a step or two ahead in a complex sequence, like poor planning. Self-verification routines that just stop too early. Like the model makes a confident-sounding assertion, maybe based on a mistake, and then its internal checker just says, yep, looks good, and moves on without digging deeper.
Oh, dear.
And crucially, a fundamental struggle to reliably follow even a simple, explicit algorithm that you give it, step by step. The basic mechanism of token prediction seems to interfere with actually executing a sequence of instructions reliably.
Wow. And this wasn't just one specific model. You mentioned they looked at models from different companies, like Claude, DeepSeek, OpenAI.
That's right. They tested several leading models, and the pattern held remarkably consistently across the board. You could swap the brand name on the graph, basically, and the fundamental dynamic, easy, okay, medium good, hard collapse was the same. Sure, one model might handle, say, 5 disks in Tower of Hanoi before hitting the wall, while another hits it at 4. But the wall was always there, and the fall off that cliff was just as steep for all of them.
And all those extra tokens generated by the chain of thought models, especially in that middle sweet spot zone. Tokens aren't free, right? There's a cost.
Not at all. They cost compute power, which translates directly to energy consumption and, well, money. The study really highlighted this. On the simple tasks, those non-thinking direct answer models use just a fraction of the tokens, sometimes orders of magnitude fewer to get the right answer, compared to the verbose chain of thought models that were, in essence, overthinking the problem.
So being economical with tokens isn't just about efficiency. It's also potentially about avoiding errors. Fewer steps means fewer opportunities to mess up.
Precisely. More tokens, more thinking doesn't automatically equal better thinking, especially if the underlying logical mechanism is brittle. Sometimes more steps just mean more chances to go wrong.
Okay, this brings us back to why these puzzles were such effective diagnostic tools, these AI X-rays, as you called them. Why not just use standard benchmarks, like math tests or reading comprehension?
That's a great question. Because those popular common benchmarks can suffer from leakage.
Leakage?
Yeah. Large models are trained on absolutely vast amounts of internet data. It's possible, even likely, that they've simply seen the answers or the specific patterns from many common benchmark tests during their training. They might have effectively memorized how to solve them.
So they might look smart on the test, but it's just recall, not real problem solving.
Exactly. But these puzzles, especially when you generate them parametrically, meaning you can create endless variations by changing the number of disks, checkers, or blocks, create novel problems. Problems the AI is highly unlikely to have encountered in exactly that form before.
Okay, so it forces them to rely on genuine understanding of the rules and the ability to generalize that understanding rather than just matching a pattern it's seen before.
Correct. In Tower of Hanoi, complexity is just the disk count. Simple knob to turn, Checker jumping scales with the number of pieces. River crossing gets harder with the number of pairs trying to cross. Blocks world arranging blocks gets factorially harder with just a few more blocks. These precise control knobs let the researchers ask a very direct question. Does the AI's ability to reason scale smoothly as the problem gets harder? Or does it just break?
And the answer pretty clearly was break.
Nosedive, yeah. It really did. And they didn't just look at the final success rate. They actually dug into the reasoning traces themselves, remember? Those long streams of tokens showing the thought process.
What did they find there?
On the simpler puzzles, they noticed something interesting. The correct path, the sequence of moves to solve it, often appeared quite early in the generated trace.
Okay.
But then the model just kept going. It kept generating more steps, sometimes nonsensical explorations, often for the rest of its allowed token limit. It was like it found the answer quickly but didn't know how to stop thinking or stop talking about it.
Huh. Like a miner who strikes gold in the first 5 minutes but then just keeps digging random holes nearby for the next hour.
Huh. Yeah, that's not a bad analogy. A bit like that. But on the harder puzzles, it was often the opposite pattern. The first part of the trace, the initial steps, was frequently just junk. Repetitive loops, invalid moves, complete non sequiturs. And if a valid path or a good idea appeared at all, it was often buried way down near the very end of the trace if it ever materialized. At high complexity, often a viable plan just never showed up.
Wow.
And this really highlights, I think, these ongoing challenges with the AI's ability to manage long-term goals, to control its own internal generation process, and to connect early actions to a distant solution that might be many steps away.
And you mentioned earlier the struggle to follow explicit algorithms. That seems really key. What happened when they literally gave the model the exact step-by-step instructions for solving, say, Tower of Hanoi and just told it, follow these rules?
It barely made a difference. The performance collapse still happened at roughly the same complexity level. The model could often perfectly describe the algorithm back to you. It could parrot the pseudocode beautifully, generate text about the rules, but it consistently failed to reliably execute that algorithm step by step when the number of steps got large, like on the harder instances of the puzzle.
That's a really critical distinction, isn't it? The ability to generate tokens that look like you're following an algorithm is not the same thing as actually reliably performing the sequence of logical operations.
Exactly. Token-level prediction versus genuine procedural execution. And for tasks where correctness is absolutely paramount, think programming, complex financial modeling, scientific simulation, that gap is fundamental. It's huge.
Right.
It shows that the verbosity, the transparency you get from chain of thought is valuable. You can see something, but it also starkly exposes just how messy and potentially unreliable that underlying token generation process can be when faced with rigorous multi-step logic.
So it sounds like the potentially good ideas or correct steps might show up early in the trace on easy problems, but they get drowned out or maybe never even appear on hard problems because the bad ideas, the errors, the loops just stick around and dominate the token budget.
That's a really good way to put it. The noise overwhelms the signal as complexity increases. And related to that, self-correction seems extremely fragile.
Fragile how?
Once the model makes a false assertion or takes a wrong turn in its reasoning, it often just builds on top of that error. It doesn't seem capable of robustly backtracking, questioning its own intermediate conclusions, or reevaluating its core assumptions once it's headed down a plausible-sounding but ultimately wrong path. The errors cascade.
So just giving these models a bigger working memory, a larger context window that doesn't fix this fundamental logical collapse.
The study strongly indicates no. More context doesn't magically install better reasoning capability. It just gives the model more room, more tokens to potentially generate those flawed steps or get lost. The failure mode they observe doesn't seem to be primarily a memory bottleneck. It looks more like a limitation in logical flow, control, and error handling.
Okay. What about some other ideas? Like, could you pair a thinking model with another AI model, a verifier, whose only job is to check the thinker's work? Does that help?
Well, the study suggests it helps a bit, but mainly in that medium complexity range.
Only in the sweet spot again.
Yeah. Once you push into that high complexity zone where the primary model falls off the cliff, the verifier model tends to fail right along with it. It seems they often suffer from the same underlying limitations when faced with deep, complex reasoning.
Is this just a memorization problem then? Maybe they've seen lots of easy puzzles online during training, but none of the really hard, complex versions.
Memorization definitely plays a role, sure. A model might perfectly ace a specific 5-disk Tower of Hanoi puzzle if it happened to see that exact solution in its training data.
Right.
But remember, these parameterized puzzles allow for generating countless novel instances. And the models still tank on, say, river crossing variants they've definitely never seen before. So the study suggests it's not just about memorization. It points more towards a lack of robust generalization and inability to truly understand and apply the underlying rules consistently to solve novel, complex problems.
And counterintuitively, you mentioned sometimes the simpler, non-thinking models, the direct answer ones, sometimes they fail later on slightly harder problems.
Yeah, because they aren't generating all those extra chain of thought tokens. They have less opportunity to introduce errors, to hallucinate intermediate steps, or to just wander down computationally expensive wrong paths.
Less rope to hang themselves with, maybe?
Kind of. It's a different failure mode for sure, often just giving a wrong final answer. But on tasks just beyond the trivially easy, sometimes that simpler approach can be accidentally more robust, simply because it's less complex internally.
Which brings us right back to that core idea, that gap between execution and explanation. That algorithm experiment seems absolutely key here. The model can explain the steps of an algorithm perfectly, but it just can't reliably do them when it gets complicated.
And that gulf is so crucial for thinking about real-world applications, isn't it? If you need an AI to perform a sequence of precise actions, maybe controlling a robot, executing a financial trade, synthesizing a molecule, you absolutely cannot just rely on its verbal explanation of what it thinks it should do.
No, you need more
You
guarantees.
need external checks. You might need symbolic systems working alongside it, hard-coded rules, or other constraints to actually ensure correctness. You have to treat the language model's output, even its reasoning trace, like incredibly helpful, fluent, but potentially error-prone advice. You still need to verify rigorously.
So this study has some pretty major implications for people actually building AI systems, right? What should they take away?
Absolutely. I mean, first, it highlights the need to be really strategic about when and how you use these verbose chain of thought models. You need to understand their token cost and, crucially, where they were likely to hit that complexity cliff and fail.
So maybe identifying if your task falls into that high complexity regime for current models.
Exactly. And if it does, you probably need a different approach. Maybe you need to break the problem down into much simpler sequential steps that stay within the medium or low complexity zones for the AI. Or maybe you need a hybrid system.
And it sounds like you absolutely need to audit the process, not just the final answer.
Yes. Don't just look at the output. Pull the reasoning trace. Check key intermediate steps. Maybe even have mechanisms like automated checks or circuit breakers designed to stop the process if it starts generating nonsense or going off the rails early on.
Auditing those intermediate states is vital.
And the study also strongly suggests, as we touched on, that hybrid systems could be really promising, combining the generative power of neural networks with the rigor of symbolic logic systems or hard-coded rules. That might be a path towards building systems that can overcome these inherent limitations of purely autoregressive models like LLMs.
And finally, they really emphasize you have to measure, don't just assume.
Yes. Don't rely only on standard overall accuracy scores from benchmarks. Collect that trace-level data. Count the tokens used. Plot those performance curves against task complexity. Those grim graphs, as the paper calls them. They might look bad, but they are actually your best diagnostic tools.
They tell you the truth about the system's limits.
Exactly. They're essential for understanding the real limitations and for figuring out how to build something more reliable.
Did the study point towards future research directions based on this?
It did. Things like how can we specifically train models to handle longer, more complex reasoning chains without collapsing? How do we get them to actually stop generating tokens once they've found a valid solution, something called adaptive stopping?
Avoiding the minor digging extra holes problem.
Right, encouraging more minimal, efficient reasoning, maybe trace compression techniques, and of course using these controlled puzzle environments not just for testing, but for actively fine-tuning models to become better, more robust reasoners. Lots of interesting paths forward.
Okay, so let's pull this all together. What does this really mean for you listening to this, maybe interacting with AI chatbots or tools every day? This deep dive into the Apple study, it gives us a much clearer lens, I think. It confirms that while these large reasoning models are incredibly capable, undeniably impressive for a huge range of tasks, there seems to be this fundamental structural limitation when the logical complexity crosses a certain threshold.
Yeah, it's not something you can apparently just fix by throwing more data at it or getting slightly faster hardware. It seems more deeply ingrained in the current architecture.
It shows that the apparent thinking we see is this incredibly powerful form of pattern matching and next token prediction, but it hits a hard limit, a reasoning cliff, when true multi-step error-reverse logical deduction is required beyond a certain depth.
Right. The kind of reasoning needed for these complex puzzles.
And as the study highlights, the good news here is that we now have a much sharper diagnostic toolkit. These puzzles, with their tunable difficulty, give researchers and builders a really precise way to identify these failure points much earlier in the development process.
And embracing those grim graphs, understanding where things break down, that's actually the necessary first step, isn't it, towards figuring out how to build more robust, more reliable AI systems in the future.
Absolutely. So this knowledge hopefully equips you, the listener, to better navigate the often confusing claims swirling around AI capabilities. You can start to see past some of the hype, maybe, and understand the actual measured limitations. It gives you a much more informed perspective, I hope, on the AI you use or hear about every day.
Yeah, moving beyond just, it works amazingly,
Yeah.
or it's completely useless,
Yeah.
to something more nuanced.
Exactly. And that leads us to a final, maybe kind of provocative thought, directly inspired by this study and its findings. The next time you hear someone confidently claim that their new AI product thinks just like a human PhD, just remember the Tower of Hanoi puzzle.
Yeah. Imagine handing that chatbot or that system a virtual version of the puzzle with, say, just 8 disks. Not hundreds, just 8. And maybe a stopwatch.
What does this study suggest might happen? If that AI locks up, if it starts generating nonsensical steps, if it just fails completely? The study suggests that failure isn't just some minor engineering glitch.
No, it highlights something deeper.
It starkly highlights the fascinating, the enduring, and yes, the profoundly human challenge of achieving true, deep, reliable reasoning compared to just generating incredibly sophisticated patterns and predictions. What does that reality tell us about the actual path we're on with AI right now, and maybe what we're still fundamentally trying to achieve?